My name is Savannah, and this is my fifth lab report for Physics 2 regarding Faraday's Law. The purpose of this lab was to work with Faraday's Law while bringing together numerous concepts that have been explored throughout the physics course this semester. These concepts include knowledge of magnetic dipoles, magnetic forces, and even ideas from Physics 1 like Newton's laws. To do well in this lab, it was essential to pay close attention to all lab directions to ensure that proper values were measured and noted. Additionally, the computational model was far more detailed, so paying close attention to the required adjustments needed in the code was necessary to ensure accuracy. Several of the key physics concepts can be seen on the right. These include Faraday's laws, Biot-Savart's law, Ohm's law, the relationship between a magnetic field and magnetic force, and Newton's second and third laws. Additional knowledge regarding gravitational force was also required. As a preview of the results, the average amount of time required to travel through the tube according to the hand-taken measurements was 0.992 seconds. The average amount of time for the bar magnet to travel through the tube according to the computational model was 0.225 seconds. This large discrepancy between the two models indicates that there may be error in the measurement taking in addition to a flawed logic in the computational model. Here is a brief overview of the lab's procedure. To begin, this lab procedure, it is necessary to acquire a smartphone, bar magnet, roll of aluminum foil, and meter stick for measuring tube dimensions. It is then necessary to mark the north end of the bar magnet, which can be done with a magnetometer app. Working in pairs, have one person hold the tube and bar magnet, and another person records the process of dropping the bar magnet through the tube. This can be seen in the video on the right. After dropping the bar magnet through the tube 5 times, scrub through the video to determine the time required for the magnet to drop through the tube. Based on the procedure above, the average time required for the bar magnet to pass through the tube was 0.992 seconds. Here is the computational model. The above shows how the bar magnet travels through the tube, while the lower portion demonstrates the change in velocity over time the bar magnet experiences while traveling through the tube. Here is the code for my computational model. This computational model had some additional questions with it that prompted some reflection following the coding process. Since the blue current is on the top, it can be assumed that the B field is pointing upwards. So the blue current is going to be counterclockwise. This would make the red current flow in the clockwise direction as the two are in opposite directions. This was based off the right-hand rule. If the magnet is flipped, the magnitude of the induced current will be the same, but the blue and red currents will now flow in opposite directions. The real-world system gave a much slower time than the computational model. The computational model could be made more accurate by accounting for air drag or friction forces that may be experienced on the inside of the tube. These two forces would lower the velocity of the bar magnet, increasing the time required to fall through the aluminum tube. The shape of the velocity first time plot tells us if the acceleration of the bar magnet remains constant or changes as it moves throughout the tube. Since the model's plot isn't perfectly linear, the acceleration of the bar magnet is changing as it moves through the tube. There is some potential error within the lab. This potential error is likely due to human error. The first error would be incorrectly reading the timestamps while scrubbing through the videos or inserting the magnet with an initial velocity, which could affect the speed within the tube. Other errors could come from the aluminum foil tube having a slightly deformed shape or not being evenly wrapped around the tube. This could affect the magnetic force that is acting upwards on the bar magnet. To conclude, these questions brought together the main concepts presented in the lab. If the resistivity of the conductor was reduced to near zero, this would increase the amount of induced current based upon Ohm's law. This increase in current would increase the magnetic force, which would decrease the speed in which the bar magnet falls through the tube. If holes or slots were cut into the tube, there would be less loops for the current to be induced through, which would reduce the induced current. This would reduce the magnitude of the magnetic force, which would increase the speed in which the bar magnet falls through the tube. A ferrous pipe, like steel, is an alloy of iron and other nonmetal elements like carbon. This would reduce the conductivity of the pipe. If this conductivity is lowered, the induced current would be adjusted, and there would be a minimal effect upon the bar magnet as compared to how it acts outside of a tube. The magnet outside of the tube, falling in free space, is only afflicted by the gravitational and air drag forces, while the magnet in the tube is experiencing an upwards magnetic force from the induced current, which lowers the speed in which it falls. Thank you.